Hello, my name is Muhamad Hafiz bin Aziz. Today, I will present about the final year project with title Multi-Objective Design Optimization of Square Tube with Circular Ring Filler using Response Surface Methodology more focused on face-centered CCD. For your information, my supervisor is Dr. Hafizan bin Hashim. First of all, the introduction. Square tube is a thin wall tube that widely used in automotive structure and aerospace industry because of their characteristic, which is energy absorption useful for engaging with collision or accident. Recent study by H. Nika et al. In comparison to the window tubes, the simple tube had a higher SEA and a better deformation mode. For the study on parameter by Zoli et al. Found that the thickness of the field structure and the thickness of the wall have a substantial impact on the SEA and PCF. The objective of this project is to optimize the specific energy absorption SEA and crush force efficiency CFE of the square tube with circular ring filler using response surface methodology, face-centered CCD. The behavior of square tube will be analyzed under 3-point bending. Therefore, the 3D model of square tube with circular ring filler need to be created for the simulation in Abacus software. Scope of work. 3D model of square tube with circular ring filler was constructed. All the material property for the model was declared in the software to improve the simulation result. Adjust the circular ring filler parameter based on the design of experiment DOE obtained in Minitab software, and the simulation of 3-point bending on the model was run. Calculating the response value, which are CAE and CFE, using the data of deflection, displacement, and force applied obtained from the simulation shown in Figure 1. The optimization of response value using RSM approach focus on face-centered CCD assisted by Minitab software. Comparison study on optimization data from the Minitab software and simulation result from Abacus software. Next, we go to the project methodology and data analysis. First of all, 3D modeling and simulation. The model of quarter of square tube with circular ring filler was created in Abacus software, as shown in Figure 2. The design build is 1/4 of the whole model because the model is symmetry and to reduce the computational time. The length of the model is 150 mm with thickness 1 mm and 50 mm height. Meanwhile, the circular ring filler height is 48 mm, 20 mm radius, and 1 mm thickness. The material utilized in the simulation is shown in the table 1. The main material used is aluminium for the square tube and the circular ring filler, and mild steel for the support and indenter. Response surface methodology. The response surface methodology is a step-by-step technique that could be summarized as illustrated in Figure 3. The input parameters selected were thickness, diameter, and height of the circular ring filler. The response parameters for the study were SEA and CFE. The design of experiment DOE was obtained using Minitab software shown in Table 2. Then the parameter that obtained from the DOE was used to adjust the model parameter for the simulation. From the simulation, the displacement of deflection and force applied was tabulated, and the SEA and CFE were calculated using this formula. Specific energy absorption, SEA, the M stands for the mass of the model without the indenter and support, while EA total is the energy absorbed by the structure during deformation. Crush force efficiency, CFE. The F stands for the force applied on the model during the simulation of the 3-point bending. The F mean obtained by trapezoidal method in MATLAB software. Then, regression analysis using the least square approach was performed to obtain the polynomial coefficient of the empirical function between the 2 response and 3 input parameter. Then, the optimization will obtain assist by Minitab software. Lastly, comparison study will be done to know the percentage error of the optimization result. We go to project finding. Firstly, design of experiment. The design of experiment obtained with simulation results were tabulated based on the table 3. These results were used to establish the empirical model. From the result, to adapt the simulation finding, a second-order model was utilized and a regression analysis using a least square approach was performed to obtain the polynomial coefficient of the empirical function between the two response and the three input parameters. The regression equation of SEA obtained is this, and the regression equation of cross-force efficiency obtained is shown below. Analysis of variance, ANOVA. The table 4 and 5 show the ANOVA of SEA and CFE. For the ANOVA of SEA, all parameters was significant, but for CFE, the thickness and the diameter are not significant. This shows the two parameters has minimal impact to the CFE result. Thus, the new simulation need to be run again, adjusting only height of the circular ring filler. This result was tabulated and shown in table 6. From the table 4, the highest p-value for specific energy absorption is diameter with 0.032 but still in significant range. The value of R squared is 98.64%, which is quite high. It shows the factor of response surface model accuracy is high, and according to traditional response surface methodology belief, this contributes to experiment improve fitness nature. Next, analysis of response surface. Response plot and contour plot is created to show the relationship between the input parameter and the response parameter. The figure 4 shows the influence of thickness and the diameter on the specific energy absorption, while figure 5 shows the influence of thickness and height on the specific energy absorption. Based on the figure 4, the maximum value of SEA when the thickness of circular ring filler value is high while the diameter value is low. Figure 5 shows the relationship between the SEA versus thickness and height. The value of SEA is at its maximum when height and thickness value is high. For the crash force efficiency, the surface plot and contour plot cannot be illustrated because of the input parameter is only had one, which is height. So the linear graph in figure 6 illustrates to show the influence of height on the crash force efficiency. Next, we go to optimization. The figure 7 shows the optimization plot of the specific energy absorption SEA and the crash force efficiency CFE. The maximum response value being prioritized for the optimal value for the specific energy absorption and crash force efficiency. The value of thickness and height of the circular ring filler need to be high to maximize the value of specific energy absorption. Meanwhile, the small value of diameter of the circular ring filler gets the maximum value of SEA. For the CFE, the minimum value of height is the maximum value of the response. The value of height gives different effect to the response. So the Minitab software suggests 44.444 mm of height for the optimal input variable for both response. Table 7 show a comparison between simulation and response surface model after extracting the data for the stated sample. In addition, the difference in outcome was estimated based on the experimental findings. There was a good compromise between all approaches with an approximate accuracy of 6%. Lastly, conclusion. As conclusion, the multi-objective design optimization of square tube with circular ring filler has achieved its objective. The 3D model of square tube with circular ring filler is developed in Abacus software to run the simulation for collecting the response data, which is SEA and CFE. Other than that, the comparison between simulation and response surface methodology show a good compatibility of two methods with approximate error 6%. If there are questions for my presentation, please contact me through my phone number or email stated below. That's all from me. Thank you very much.